regulatory requirement. So the project requirement is all around how do we make sure that the project is running on time, on schedule, to budget with the minimal number of delays. Our operational goals, they're all around how the operations team view and perceive the safety risks, how do they ensure that their plant is up to spec and it's safe to operate. And then for the regulatory component, this is where it might be the government is asking us to perform an inspection to prove to them that we are fit and able to operate and that our asset is not going to blow up or we're not going to have a Deepwater Horizon incident like we see out of the States every couple of years. So when we perform inspection, we ourselves have a number of goals that we have to perform and that we have to achieve. So our primary objective is to help collect and gather the data for our client, obviously. We need to record it, document the condition, both good and bad, as accurately as we can. Because if we've seen an area that's a good representative sample of, say, the shell in a pressure vessel is not corroding, it's okay. We want images and data of that. Because 3 years down the track, they may have an incident and they will look at this data and go back and go, oh, this was good back then, or no, it wasn't, and they'll start to compare the results that we're seeing. So the more good information we can get them on the good condition as well is really important. We want to be providing multiple images or data sets for UT or visual inspection, and those images need to be in focus because they're going to sit there on their computer screens and they're going to zoom in and blow everything up and pixelate everything. So the clearer and sharper and more in focus we have those images and data sets, the better it is for the clients to be able to do post-inspection analysis. Once we've started to identify our goals, we need to start to look at the asset or the inspection in question. So if we're, say, looking at a separator, how we approach a vertical separator might be slightly different to how we approach a horizontal flare drum, etc. So, and then we need to look at why are we doing confined space, what is the purpose, and start to assess how we get there. Robotic inspection in the field to physically complete it can take longer and generally does take longer than putting a person in and climbing around inside to do it. But where all the savings are made, as you can see in that graphic, it's a much more linear line from start to finish. Our front-end planning can be a lot less, the operational requirements and setup and safety requirements for that can be a lot less. The data that's captured and gathered can be processed, annotated, analysed and reported on much easier, and we obtain much more levels of data through a robotic inspection process. So we have to start asking ourselves when we start to look at this is we want to see the general arrangements of the asset. Because some robots are a vacuum crawler, so they adhere to stainless steels very well. Our robots, such as what we have in front of us, is for use on ferromagnetic surfaces. So if we're in a pure stainless steel asset, we're not going to be able to operate too well. Is it clean or dirty? Because doing UT or visual inspection on a dirty surface is going to give us different results. What we then also want is we want process and instrumentation diagrams. So what is our process like? Are we going to have what deposition is known through this asset? Cleanliness is always a big one for us. Because we're not looking to put people inside, we have to look at different ways of cleaning. So whether through steam, chemical, or sitting from the first access point with a hose and water jetting from the outside to wash all the deposition away. In some instances, we are going to have areas of deposition that is going to accumulate at the bottom of the asset, much like we see here, that we physically can't remove. In this case, we would actually look to do corrosion mapping from the outside to ensure the integrity of that asset, and we can still operate the robots from the inside to go around and do our visual and other EPT inspection aspects where it's nice and clean. So we're using a hybrid type of approach. Once we've done our assessment, we've determined the types of robotics that we're going to use and the way that we'd like to do it, we start to build up our scope. So in most cases with robotics, you'll start to build a digital twin. So either a 3D model, a CAD model, a point cloud, or a laser scan. We then start to work out our most efficient driving path through that asset. So we want to know which way we're going to drive through, because we can get lost very easily. We can get the umbilicals and cables caught up on the internal piping quite quickly. This is also going to help us identify key areas we need to get to and how we're going to get to those key areas. Once we've done that, we would build up an inspection work scope. So this is the work pack. This is the bit of paper that you have with you in the field that says go to here, do this, go to here, do that. We would build that up, the client would build that up, and that would be handed out to the inspection teams. Once we've done that, we then obviously go to site, we do the inspection, we capture the data. When it comes to robotic inspection, how we capture that data is really, really critical. We don't want to be jumping around all over the place, going from, say, that corner to that corner to that corner to that corner, because people get lost and confused. When you're reading the report at the end, the image looks unstructured and the chances that you've missed something is a lot greater. So we want to be working in a methodical manner, such as like you would read a book. So perform the inspection from top down, left to right, or from right to left. But once you've chosen your appropriate inspection task or method or way that you're moving, stick to that for the entire asset. Documenting our data is really critical. If we've mislabeled images or NDT data, it can give the client a false representation of what's there. A nozzle that might be called K1A that we've labeled N6 that might have corrosion, the client might actually go out and remove that nozzle, cut it out, and replace the wrong nozzle. I've seen this happen many times in the industry, once in New Zealand where they cut the wrong nozzle out thinking it had hydrogen attack, and it was actually a different nozzle.
Baik, teman-teman semuanya, Bapak-Bapak, apabila ada pertanyaan, ini seperti bukan hanya one way satu arah, kita pengennya lebih diskusi. Jadi kita juga pengen tahu sebenarnya aplikasi apa sih di nuklir ini yang agak kesulitan untuk mencarikan solusi, misalnya apa gitu, ada buat yang ini bukti tapi kok alatnya kita belum ada nih yang membantu mereka seperti ini.
Saya ulangi lagi, jadi bukan hanya satu arah session ini, kami harapkan bisa dua arah. Jadi mau di stop di bagian mana aja silakan, karena insya Allah bisa membantu apa sih yang kita masih kesulitan dan kita bisa cari solusinya di sini. Cepat tahu ada solusi yang bermanfaat bagi kita. Jadi ada pertanyaan sebelum dilanjut ke reporting? Karena kita udah 15 page. Pertanyaan Pak, teman-teman?
Ada nggak yang mau ditanyakan?
Masih lanjut dulu ya.
Lanjut.
So once we've collected all our inspection data, we obviously need to report on it. Our reporting, sometimes this is the most important step that we have. Obviously, as I said, recording and capturing that data, annotating it, making sure it's captured methodically and correctly, and then reporting on that. I've been involved in a few court cases personally where our inspection reports have gone through US court systems, and one of the largest warranty claims was $500 million US. And the way that we captured and recorded and structured that meant that it was a lot harder for the defendant to argue that we had falsified or that the inspection hadn't been completed with integrity. Analysis, so once we've done the inspection, the client's going to want to do their own post-inspection analysis. So having the clear data enables them to do this correctly. It also means that we can find lessons learned areas to perform the inspection faster, more efficiently, and gain more time and capture better data. So where do we, as Waygate, fit into all of this? So we build a number of different platforms and technologies to be able to go through and capture and alleviate a lot of these problems for us, or start to automate this. So within our technology portfolio for our robotics team, We've got our bike platform, which is just in front of us. So this is an ultra-mobile robot that is a delivery platform. It is designed to navigate through complex environments, through different types of structures and geometries. We can transition from horizontal to vertical and back to overhead again with the magnets and the way that the robot works. We have the new Zoom HD, which is a large space or large area visual camera. So for doing large pressure vessels, storage tanks, gas spares, things like that. We then have the HD pole, or sorry, the 3D lock pole. So this is being able to attach the camera to the pole and give us 3D localization within an asset. So we know at all times with our digital twin where our camera is pointing, what we're looking at, and when we capture that data, it geotags that data to the 3D model. And this is the 3D lock system. So this is the software, the 3D digital twin, and our reporting aspect that all of our platforms tie into to give us a digital twin 3D model report with all the data geotagged to locations.
Ya, teman-teman dan bapak-bapak sekalian, jadi saya mendapatkan informasi juga bahwa beberapa tahun yang lalu itu ada tim ANSTO, Australian Nuclear Association, itu menggunakan alat seperti yang Zoom HD itu, tapi dia masih yang lamanya, itu namanya Zoom 140 dan Zoom 120 kalau nggak salah. Ya, dan itu sudah discontinue. Nah, yang barunya itu adalah Zoom HD dan dilengkapi dengan 3D lock pole dan menggunakan 3D lock untuk bisa melakukan measurement dan juga 3D drawingnya. Dan ini sangat membantu sekali. Dan pada saat itu dari tim waktu itu masih Batak, kemudian ya waktu itu masih Batak, itu apa namanya, hasilnya bagus gitu dan impresif sekali. Nah, ini sudah di-improve oleh tim R&D kami dari WNT Technologies, jadilah seperti ini. Nah, sekarang itu perkembangannya, dan sekarang yang baik platform ini adalah suatu improvement lagi yang bisa mengcombine bukan hanya visual tapi IoT juga bisa dipakai. Ada pertanyaan mungkin? Ya, Mas.
Ya, untuk yang 3D Zoom ini tadi, itu untuk minimal pipe-nya berapa dimensinya? Apakah ada minimal pipe, kemudian maksimum pipe-nya berapa gitu?
Oke, kalau yang untuk Zoom ini selama aksesnya itu masih bisa masuk dia boleh.
Terus untuk panjangnya tadi tuh? Itu kan bisa panjang itu ya?
Oke, panjang dari pole-nya itu maksimum 4 meter.
4 meter ya? Oke. Dia dibawa oleh si back platformnya atau dia memang separate, terpisah sendiri untuk aplikasinya itu?
Untuk
yang kayak Zoom tadi? Itu apakah bisa ditumpangkan di backnya ini, robot ini, atau memang dia sendiri, kita install sendiri untuk
Oke. For Zoom, it can be used with back platform or what?
No, the Zoom does not mount to the robot platform. While it's within the weight limit, the torque and the leverage that's applied to the robot when it's mounted at the top starts to have an issue with the magnets and the way that it operates. So that's why we have a smaller tilt zoom camera on top that's an HD, so we can run different systems.
Oh, oke, okay.
Jadi beda
sistemnya. Tapi untuk software ya, untuk 3D lock-nya itu sama ya? Sama ya.
Itu bisa dipakai di Zoom.
Ataupun
for the 3D lock, it's the same PTZ and byte.
Yes. So the way that they do their localization for each, either the Zoom HD or the bike, the way they do the localization is very different, but it's all compatible from the same control station, the same model, the same everything. All the data, if you've, say, done an inspection with the pan and tilt and the 3D model localization, you can quite literally unplug the camera, plug the robot into it, calibrate the robot to the model, and it will keep adding that data to the same model that you started with. So it's all compatible with one complete system.
Oke. Untuk drawing modelnya tadi dari mana, Pak?
Okay, for the drawing model, we just need the.
We're gonna get through that, yes.
Okay.
Okay.
Kita akan.
You're jumping ahead about 6 slides, but it's good to know that that's where we're going.
Mungkin kita teruskan. Terima kasih Mas.
So, as I said, the bike robot is a highly mobile inspection platform. As you would have seen in the video, it can crawl over 90-degree obstacles, so both concave and vertical. We can hold up to 5 kilos upside down. We can hold more if we're flat or on the side or traveling in a vertical motion. If we're starting to go horizontally, that changes depending on the physics. Within the robot itself, the base platform, as you see here in front of us, we've got a forward-facing tilt-zoom camera. So this bit here, or the blue section on top. So this is a camera that goes up and down and is in full HD and has integrated lights in it because we need to be able to adjust and control our lighting when we're looking at an area. We've got forward and rear-facing fisheye cameras, so they can see about 220 degrees. So we can see the front wheels in the robot, the side, on both the front and the back of the robot. So we've got it on the back because when we're driving through areas, we need to be able to see what our tether is doing. Have we got it caught on some internal piping? Is it caught on a vortex breaker, etc.? We've got a basic spot testing thickness probe mounted between the front wheels, which is water actuated. So when we apply water pressure down through the umbilical cable, this then pushes the probe onto the surface of the material. The overflow of the water then acts as our coupler. And then when we want to retract the probe, we create a vacuum in the line and the probe lifts up off the surface. Now, that's the basic NDT. We've got other roller probes. We can do EMAT with other different attachments. We can do eddy current array. So if we're looking for cracking in welds, so instead of doing MPI, magnetic particle inspection, we can use eddy current array to go and create digital maps of these. One of the other extras that we have here is doing foreign object search and retrieval. We've got a 5-function manipulator up. Now this is the same type of technology that they use on subsea ROVs, only this is now miniaturized to be able to attach to our robot that we control with basically an Xbox or a PlayStation controller or Nintendo. If you're familiar with Nintendo controllers, we can mount it and use those types of controllers to operate the arm and go through and pick up components. And I've got some videos that I'll show you later on of that working. Because the hardware is designed to move and operate through different types of environments, we can rewrite software quite quickly to give it structured measurements or structured movements. So in this instance here, we're doing some very basic forms of corrosion mapping with the roller probe, or more effectively, it's just continuous line scans in a B-scan format. So this is our 3D model of our test mock up in Switzerland. And we can see here that the robot self-drives itself backwards and forwards. And we attach the pen, we take the pen inside of it so we can see the movements it was actually doing. So we can pre-program this in the field on the fly, just through 3 or 4 quick simple buttons, and that's it, nice and easy.
Sorry, a little bit question. Untuk yang tadi scanning itu ya, scanning itu untuk lebar jalurnya, pergeseran scannya itu reprogrammable ya, iya kan?
Yes, it's a program. We can choose the length, the distance between the scans, and then how wide we want the total scan. So we can go, we want the scan, say, to be 300 by 300, and then every 5 millimeters or 10 millimeters, we want it to take a reading. And when we set up and we start to play with the robot, I'll actually show you, and we can have it do that on the floor. Hopefully there's enough traction with the tiles that it works. And this is our eddy current inspection. So we've got another arm that mounts to the robot that again is fully controllable from outside of the system, from outside on the control station. And from here we can mount different types of tools. So if we want to put on phased array or Toft or eddy current array or PEC or some other form of tool, all we have to do is 3D print up a bracket that holds that, and we can go and perform those inspections. And then we come to our Zoom HD. So this is our large area visual camera, which I haven't set up just yet. We'll pull it out of the box soon. It's all controlled by a tablet. So effectively a Panasonic type tablet through a very small interface box and then out to the camera. We've chosen the tablet because when you're in the field, you want to have access to being able to do your reports at any given time. So it's a Microsoft Windows tablet. You can install Teams, Word, Excel, search the internet, do any of your web-based reporting stuff from there, as you would use any other form of Microsoft tablet. And then we can also operate and control our camera system from it. When we get to the camera itself, it's fully articulatable, so pan and tilt. So it'll look up and look down, and then it can rotate around zoom. We've got 30 times optical zoom in full HD, and then we've got 4 massive 9-watt LED lights, which are incredibly bright. If you look at them for any more than a second while they're on full brightness, you can blind yourself for a couple of seconds when you look away, as I did yesterday. We've got laser lines for doing surface measurement. So if we've seen an area or we want to roughly work out how big that area is, we can take an approximate size estimation. Now these are not for doing depth measurements of pits or cracks or surface profile. It is an approximate area surface measurement only in a 2D plane. So if your vessel's curved, it's not going to follow the curve of the vessel, it's only go from point A to point B. So you might be out by a little bit, but you'll get a rough size estimation of what you're looking at. And this is the 3D lock pole. So this is where we can either take the pan and tilt that we've got and mount it to this, or the pan and tilt can be mounted to another form of delivery tool. This helps us work out where we are with a fixed camera in a 3D space. So going to your question of 3D models, how do we take our 3D model and then how do we put it into the system and match the hardware and the software up? Well, to start with, we would either look to use an existing CAD model that a client has.
Okay.
So if they've got a 3D model of their asset, we can take that, we can pop that in our system. If we've flown, say, an Helios 3, used a Faro or a Leica point cloud scanner, we can take that point cloud, we can mesh it on the control station of our software, and then we can drop that straight into our operating system for our robot. Or we can alternatively use what we call Asset Builder. So this is an online web-based tool made by a company called Quasset, and it's effectively Lego for 3D pressure vessels. So we just drag and drop different applications as we need them. And again, we'll show you how that works just after this, because we can build a very simple vertical separator in about 5 minutes. Once we've built and generated our 3D model, we can then perform a simulated inspection. So this is where we drive around in a theoretical simulator, see what we can get to, work out if we can or can't get to things, or if they're going to pose problems, or if the robot falls off the wall in the simulator, that's where we're going to fall off in real life. And once we've worked all that out, we come to our actual inspection. And this is an example of that entire process for Shell in the UK. So this was an inspection that we did on a vertical salt dissolver tower. So we come through multiple different access points with the robots to perform this inspection. So this is building it using the 3D model, using the Asset Builder online tool. We're now checking the model to ensure that for its accuracy and matching up our work scope areas for inspection. Once we're happy with that, we then move into our simulated inspection through here. So we choose our vessel, choose our inspection tool, our deployment point, and now we get to play video games. So in here we've got full control over camera and lights, and we can see what's going on. And once we're happy with that, we start to go perform our inspection. So with the simulator, we can also use it to train the technicians on the path that we want them to follow, or the way that we want them to perform the inspection.
A question, sorry. After we have a 3D model in here, we can define the route of the robot, or we only just use the free move?
We can't define the route of the robot just yet. That comes into artificial intelligence and machine learning, which is something that we are working on in our workshop in Switzerland, but it's not something that's available or allowed. I can share right now.
Okay.
Jadi kalau misalnya lu masuk ke dalam, kalau ada drawing sebelumnya, dia bisa menunjukkan kalau misalnya ada defect di sini, dia langsung tagging gitu. Tagging. Jadi kita udah tahu posisinya di sini, ini.
Tapi kalau arahnya, jadi kalau udah punya gini, kita ingin inspeksinya nggak kita kendalikan gitu, tapi ya pengen muter ke sini gitu loh. Apakah itu sudah diprogram atau memang kita kontrol dengan joystick gitu? Joystick ya, ya kan, belum yang dengan route-nya kita tentukan belum ya? Oke. Iya, maksudnya gitu.
And this here is just a video of what we see when we perform the same type of inspection with the camera and the 3D lock pole. So we can see where the camera is looking, where it's moving to. Now each of those blue prism points are a data set. So every time we take an image, and you'll see very soon we take this image here, that data set gets tagged to that model. Once it's tagged to the model, it's there for the entire life of that model. And we can recall that at any given point in time.
That's tagged by human or by system? Okay, yeah.
Manual. It's all manual.
Manual, yeah.
Dan ini hasil dari 30 kali zoom, optical zoom.
Optical. Tinggi ya itu ya. Cukup ini. Iya. Berarti ketika kita udah tahu, oh ini ada cacat, kita tag langsung bisa tahu posisinya ya. Oke.
So just summing up what we've covered through. For successful inspections, we want to define our plans, our goals, and our objectives. Our inspections need to be planned and assessed on their merits and with the tools available or the type of tools we intend to use. Because stainless and carbon steel require very different approaches. Our execution and infield plans need to be developed and need to be accurate and highly detailed for us to go and do what we need to do, because robots don't think like people. Our reports need to be ensure that they're clear, detailed, concise and accurate, and we want to be able to review and analyse all our inspection data post-inspection for further improvements and to help our clients out with their asset integrity management plans. So I'm going to show you guys a sample inspection that we've done using the 3D model, and we're going to walk through the inspection, play with the model, show you how it all works and what the deliverable is at the end. Yes, so this software here is proprietary to us, but it is free to download. And we do have sample missions or sample inspections on our website that you can download and play with and have a look. This only works with our systems, however, it doesn't work with any other company's robotic platforms. So what we've got is we can see our pressure vessel here. We can then cut it open and we can start to see the internals of it and any other aspect that we've got. Down the bottom here we have our inspection timeline. So at every given point in time, all the data and the metadata from this robot is recorded and captured. The steering angles, the light levels, the zoom, where the robot was, where it was looking, where it was facing, all that stuff is recorded. Because what we're trying to be able to get to for our next step, in say 3 years' time, is put this robot back in through the same access point, push start, and it goes back and repeats that exact same inspection, the same locations, the same lighting level, the same zoom levels, to give us that repeatable and comparative inspection, which starts to lead us into the automated inspection, being able to pre-plan that in that simulator, so that whatever we drive around that simulator, it does the same thing. We then take that mission and push start, and the robot goes and does the inspection as we've programmed it to do. So, as I said, at any given point in time, this robot knows where it is, and as we scroll through, you'll start to see it moves around. Each of these prisms is our data point, which we can click on, and it will show you the location of that robot, where it took that data set, where the robot was, where the camera was looking, and what that is of. If we want to look at any of the UT stuff, we can click on the green prism points, and it shows us our UT scan. So we have no ambiguity, no grey areas about whether the technician could write a 6 or a 0, because I'm notorious for that. So there's no misinterpretation of the numbers in the reports. You get the A scan and the digital readout that shows everything that was recorded at that time. If we want to see some other forms of NDT, we've actually mounted a digital pit gauge to the top of this. So we were going through doing surface profiling in some areas and looking for pits, or measuring the pits using structured light technology. We could then create a heat map from those scans, and also our visual surface profile as a picture.
Ada yang mau ditanyakan mungkin teman-teman? Nggak apa-apa, tanya aja. Silakan.
Itu jadwal kabelnya berapa ya?
Iya.
Itu operasionalnya pakai kabel ya?
Iya, pakai kabel yang ini.
Paling panjang berapa ya? Apa sesuai proyek?
Juga sama, 45. Ini yang kedua sama bawahnya.
So,
Oh, ini harusnya nama.
the maximum cable length is determined by the type of inspection that we're doing. So if we're running the standard UT Pro setup as you see there, we can run up to 30 meters, because UT signal gets lost over the lead length, and we struggle to pump the water any more than 30 meters from that. If we're moving to say an EMAT or an eddy current technology, we can run up to 60 meters, 65 meters, and then if we want to start running over that distance, we have to go from copper over Ethernet to fiber optics. Does that make sense?
Ya, karena untuk yang UT kan, kalau misalnya makin jauh, pulsanya makin hilang. Jadi maksimum untuk itu 30 meter. Dan juga kita kalau untuk UT, koplonnya itu kita pakai air. Jadi kita ada pompanya, itu ngepump gitu, itu nanti keluar air di bawah itu. Dan kita dikembangkan juga apa namanya, koplernya itu
So our roller probe that we have does require a little bit of water, but that helps to give it a better surface contact. But that's still in development.
Kita lagi development dan kopler juga, tapi masih membutuhkan air. Tapi airnya hanya di awal aja, nanti setelahnya kita nggak pakai air. Jadi menggantikan si airnya itu. Oke, dari teman-teman, ayo. Ya, silakan.
Thanks to Mr. Khan. I have two questions. So the first one is, how long does it usually need to be maintained starting from the magnetic force on the wheels or other robotic parts such as robotic arm or cameras? And then the second question, is there a periodic calibration to maintain the precision of the robot?
I can answer the second one because I heard that one more clearly. No, we don't need to have any calibrations for the localization of the robot. There's 9 IMUs within the robot itself. Each wheel has its own IMU controlling the motor, which helps to do the encoding. There's a forward-facing, rear-facing, up and down, pitch and roll, IMU as well, so each of those. And then the remaining 60% of the localization is done through a LiDAR module on the top, which emits a LiDAR ray and calculates the time it comes back and works out where it is in the confined space. Could you repeat the first question as I didn't quite hear you?
Untuk maintainnya, misalnya
Can we give him the mic? Can we give him the microphone?
Okay. How to maintain the permanent magnetized wheel? Permanent magnet wheel. How to maintain? Bagaimana merawatnya kalau?
ya kayak kan papat robot itu biasanya ada kesalahan sistem atau sebagainya gitu. Apa ada mungkin tentu berkala gitu. Ada proses
Perawatan berkala kan.
Just special treatment to maintain the wheels because
Duct tape.
yeah, this is the magnet.
Duct tape.
Duct tape.
Duct tape. So we would clean the magnetic wheels with a brass wire brush, and then we use duct tape to pull off any remaining debris, and that's how we clean it and look after it. Duct tape is a wonderful thing. It's even in all our training videos showing the guys using duct tape to clean and look after the wheels.
Is there a possibility the magnet permanent is decreased for power?
Not over time, no. We haven't seen any magnetic decrease in power or magnetic force in the years of development that we've had with this. The only issue that we see with magnetic decrease is as the temperatures go up, the magnetic forces decrease. I think at 180 degrees we start to lose most of our magnetic adhesion, but at that temperature you're starting to melt the solder on the inside of the robot.
How about the wheel? This is produced by your company, or we can find the wheel in other?
The wheels are made by our company. We make them in Switzerland and Germany to our own specifications.
Oh,
Yeah.
I think in the
yeah, it's patent ya.
Mungkin Mas Robin bisa share karena Sean kemarin ngobrol sama saya di perjalanan, dia juga masih belum terlalu pengalaman di industri itu aplikasi yang kira-kira membutuhkan robot atau di sini di mana. Dia belum masih sama dia karena sebelumnya dia lebih ke orangnya.
Oke.
Aviasi aja dia lebih ke orangnya. Mungkin bisa sharing ke siapa aja dan mungkin kita bisa memberikan solusi.
Ya kalau di mana di sini nanti kebanyakan di reaktor ya Pak ya. Di reaktor satu untuk mengukur ketebalan dinding reaktornya, pipa apa namanya tangki reaktor. Kemudian untuk mengecek biasanya pakai boroskop dimasukkan seperti itu ke airnya seperti itu. Makanya tadi saya tanya yang itu zoom tadi itu. Dan juga nanti untuk coolant, untuk cooling tower seperti itu. Dan mungkin teman-teman dari mana Pak tanah ini?
ini kayak di reaktor serpong itu juga ada indikasi kayak crack, cuman kan harus melihat memastikannya itu
Lokasinya ya
Dan itu harus
turun.
nyelam.
Nyelam nggak?
iya, harus nyelam di air dari reaktor.
Terus ini juga kami penasaran ya ketika nanti masuk ke reaktor air itu kan di reaktor tuh airnya sebagai pendingin. Dan ketika pendingin itu kan berinteraksi dengan neutron seperti itu. Nah saya nggak tahu nanti di reaktor gimana. Apakah nanti neutronnya itu juga masih ada di airnya itu sehingga akan berpengaruh dengan komponen-komponen elektronik yang ada di robot atau enggak. Nah, itu mungkin nanti bisa discuss dengan Pak Umar nih yang di reaktor nanti. Nah, itu saya juga penasaran itu. Jangan-jangan nanti robotnya jadi aktif kan, jadi memancarkan dari hasil ya itu.
Ya, karena komponennya jelas.
Itu.
Jadi kayak transformer ya.
Itu yang saya
Kalau perlu nggak masalah berdua ya.
kalau pas posisinya nggak ini, saya nggak tahu pas posisi dia nggak ada radiasi konsentrasi itu keluar radiasi neutronnya nggak di air. Kalau memang nggak, oke. Jadi kalau memang nggak ada, mungkin bisa aktif karena
Dia masuk itu sembarangan kontaminan.
iya kontaminasi ya. Kamu langsung nggak bisa dipakai.
Iya. Sejauh mana tadi sudah menjadi
Jadi 40 meter, Pak. 40 meter kabelnya kan yang kabelnya tadi. Kemudian kalau di luar UT bisa 60. Kalau UT cuma 30 sampai 40.
Sorry, we're trying to ask the question about the nuclear reactor. What's our access point like? How far from our access point are we traveling? What is the material of construction? What is our geometry? Because that all determines how do we get inside and out and what tools we use.
Ya, mungkin gini. Untuk akses pointnya ya, untuk masuknya sih sangat mudah ya, karena di atas langsung bisa masuk gitu ya. Jadi tangki, air, masuk gitu aja, seperti itu. Kemudian materialnya stainless kalau nggak salah ya, stainless. Diameternya reaktor itu berapa ya Pak? Gitu ya? Saya nggak begitu tahu. Mungkin nanti ke Pak Umar aja Pak, detail dimensi kemudian dan ukurannya. Karena kan dia tidak cuma stainless tapi juga ada konkrit. Gitu. Iya, mungkin sekitar 50-an senti Pak. Konkritnya itu. Steel, konkrit, iya. Jadi di steelnya dulu, konkrit. Kalau nggak salah juga ada timbelnya juga nanti. Iya. Gitu. Karena untuk gamanya nanti air untuk netronnya, konkrit untuk gamma juga. Iya, makanya kalau ini stainless gitu ya di sini.
Yeah, we can't get concrete. We can't operate over concrete. We can't operate over concrete. We have no magnetic
Yeah.
field. And we just go. And then we break something and we have bigger problems.
Zoom pakainya nanti iya. Zoom, iya.
Yeah. But the Kazoom will only do visual inspection, won't do interior.
Iya.
Yeah, it's radioactive. Yes, I understand that.
Komponen.
Yes, the radiation does affect tools. You can fry electronics with radiation doses. The questions that I'd like to know is what is your minimum radiation dosage that you require? So systems are rated to, I actually couldn't tell you the actual name of the thing, but I know that a lot of the camera inspection systems on the market for nuclear use do have a designation on how many units of radiation they can acquire in a short term and a long term.
For human? For human or for...
I know for the equipment.
Oh, for the equipment, I don't know.
Yeah, so if I know what your radiation dosages are, we can work that out. But we are doing some internal testing in the next couple of weeks for using these equipment in a nuclear environment and seeing at what point of radiation dosage for short term and long term they fail at. Yeah.
Kalau untuk dosisnya saya belum tahu ya Pak ya. Belum tahu.
Seberapa jauh?
Apanya?
sebenarnya
Akses ke bawah? Sekitar 3-4 meteran lagi ya. 3-4 meteran gitu. Iya.
Tapi dalam airnya
Ya, enggak. Jadi tangki itu 3-4 meter kalau nggak salah ya. Sekitar segitu, terus nanti udah fully water itu di sini, full water.
kan nggak mungkin.
Nanti kan mau ke sana kan juga. Bisa lihat dari di situ. Memang kalau di reaktor itu pakai periskop ya, yang untuk melihatnya, dicemplungin gitu.
Studio Pak.
Nah, itu lihat visualnya pakai borescope. Gitu. Yang manual nanti digerakkan pakai motor stepper turun tek 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 tek, tek. Nanti naik setiap 5 cm, diputer lihat, naik, diputer lihat gitu. Scanning gitu manual masih. Mungkin ya tadi cek zoom tadi.
That's most of the explanation I had on the software. We can export all this data, all the metadata, as a CSV or a JSON file. So all the coordinates that the robot has been through, where it's been driven, all the data points can be captured. We can actually export all of that as a vessel coordinate, so X, Y, and pi, or phi, I think it's called, which you can then take and put into 3D Smart Plant or other robot operating software. It's like it's designed to be open, that you can export all of that. It's not locked in here. Say we've got to get our report out to our client, we'll generate a report. Let's just call this technology opener.
How about the speed from your robot?
So the robot moves at a maximum speed of 50 millimeters per second.
50 millimeter per second.
It's not very fast, but you're trying to perform the inspection while you're moving, not actually drive from A to B as fast as you can. It'd have a different aerodynamic shape if it was trying to go from A to B faster. The other reason why we don't move that fast is because if you're driving through some areas where you might have some heavy scale or deposition, sometimes nozzles can be blocked up and you can't see the nozzles and you drive over the nozzle. So the idea is that you're moving slow enough that you don't bounce the robot off the wall and you don't damage any of the wheels or the steering sensors or that, and you've got time to slow down and back out before you've gone too far.
This is four-wheel drive or?
This is four-wheel drive, yes. 60% to the front wheels, 40% to the back.
Oh, okay.
And then when we push the full throttle, it will send 50% to the back, and if the front wheels start to slip, it will send a little bit more power to the back to push it up over thing. And there's some really clever smarts in the way the technology works with the four-wheel drive system.
Teman-teman ada yang ditanyakan?
Ada tuh, Pak.
Ini kan dijelasin kalau ada beberapa custom tool ya Pak, yang untuk dipasangkan di robot itu gitu. Nah, apakah bisa dua atau lebih atau hanya satu aja? Ya, kalau yang custom tool dipasangkan.
Kita bisa compatibility sama API. Jadi bagian bawahnya itu kita bisa pakai hook, atasnya kita bisa pakai torso.
Combine ya.
Jadi sekali jalan itu kita bisa 2 meter bisa jalan.
Dan juga langsung tertampil di tool.
Oh. Tadi sebelum ada slide juga kan ada metode ID card juga kan, karena tampilan di scan-nya.
Jadi ketika tadinya cacatnya ini kita bisa tahu secara visual dan juga pada saat duty-nya tadi ya ditunjukkan.
Tadi ada tampilan scan-nya juga kan.
Iya.
Kayak ruang sidang. Batannya istilah ruang sidang.
Nggak tahu dia.
So this is our report that we just generated from our software that shows the image and all our locations of inspection with all our coordinates, etc.
Untuk pencahayaan lampunya itu bagaimana ya? Artinya ketika dia melalui pipa itu kan ternyata kan lorong itu kan gelap ya.
Iya.
Nah, itu nanti pencahayaannya bisa diatur nggak?
Di depan itu ada LED sama set. So buat light for the inspection.
The LEDs integrated into the cameras and the robot themselves. So we can control, adjust the intensity and brightness from the outside.
Bisa diatur.
Bisa diatur ya.
Sesuai sama.
Betul. Karena kan kalau nggak bisa diatur, dia terterang ketika mendapatkan nggak bisa objeknya jadi nggak bisa gitu. Nggak fokus. Ya.
Nanti dicontohin Pak ketika menemukan bukan defect atau kita mau fokusnya di mana, dia nanti akan otomatis fokus nanti ke cahaya.
Oh iya.
Kita bisa ngatur untuk ngatur di brightness-nya juga, ngatur ketika menemukan anomali gitu kan.
Iya, iya.
Jadi akan auto fokus.
Auto fokus.
Nanti bisa dicoba.
So what we'll do now is we'll create a quick vertical separator, much like you would find in any LNG facility or other gas plant. So we've got our shell, we'll make that 6 meters tall. We've got our heads on top, heads on the bottom. Here's our manway. So we can adjust our manway sizes, dimensions, etc. We're going to make this 1200 from our bottom section at 90 degrees.
Iya.
We're then going to put our inlet nozzle in. Let's go 4,000, which is a good number. We're going to make that 750 millimeters diameter. And we want that at 180 degrees. And we want that to be at 750 diameter and 1,500. Here's our inlet device. Put our demistomat in right now. Here's a demistomat. Put our vent nozzle at the top. Put our drain nozzle in with an elbow. And then we've just built a basic separator vessel in 2 minutes. And all we have to do is start adding in our level transmitter nozzles and everything else that might be on that vessel, which we can then export as a different file type. So for our system, we would be using an STL. We would export that as an STL file type, and our system would recognize that. Do we want to have a 5-minute break before we start playing with the robot?
Kita mau langsung aja atau mau
Break dulu 5 menit.
5 menit?
Break. Oh, pertanyaan.
Monggo Pak.
Kalau itu bisa untuk spek karena satu juga nanti bisa menawar poin bisa ada yang belum ini harus yakin
Di swab.
spek scan meningkat cara menyeluruh satu perkembangan untuk dalam dari tabung tadi. Jadi kita kamera ditaruh bisa menswab seluruh permukaan pesawat dan terjadi kelainan.
Oke. Kalau langsung semua belum bisa Pak. Nah, karena kalau pakai yang pen ini yang satu lagi ya, itu cuma muter. Nah, itu secara visual bisa. Kalau yang ini belum bisa. Dia harus benar-benar scan jalan sesuai dengan drawing yang tadi show. Kita udah drawing, nah itu kita bisa. Jadi kalau yang PTZ, yang kayak zoom itu, yang kayak zoom flash, SD, ya itu bisa. Kita tinggal taruh aja, masukin dia di tengah-tengah peselnya. Nah dia kita tinggal putar Pak, karena dia pensil sama dia 360 juga bisa. Dan dia waktu itu zoomnya 30 kali, jadi kita kelihatan bisa. Misalnya kita dapat anomali di zoom, itu kelihatan, dan letaknya pun kita juga bisa mengetahui dalam kamera zoomnya dari atas gitu, ada kan yang menyebar itu adalah infrarednya dan cahayanya itu mencari anomali-anomalinya kita mencari. Kita tetap masuk. Iya. Nah, dan sebelah sini remote.
Ini kazumnya di bawah nggak Pak?
Ada, cuman sticknya enggak.
Oh, oke. Itu sticknya itu kayak tripod gitu atau gimana?
Iya, kayak tripod. Can you show the phone? Iya.
Oh, oke.
Jadi dia ngegantung. Iya.
Yes, 4 meters extension only.
Itu apa namanya, settingnya itu harus di center atau bisa bebas saja, misalnya kan ada main hole-nya gitu, apakah dia center main hole itu ketika setting atau bisa agak kegeser? Bisa ada masalah untuk 3D-nya nanti?
Iya, nggak masalah.
Oh, ada laser tadi ya untuk metode-nya ya.
Iya, memang tetap sama Pak, satu kontrol sistem. Ya, itu. Sekarang mungkin kita ya, harusnya dulu.
Udah selesai tripodnya.
Silo ya.
Lampunya jelas ya.
Terang banget ya.
Tes di mana?
Udah, yang ada nih. Kalau dikasih lagi nggak apa-apa.
Bukan ini dianggap cacat.
Kalau dikasih lagi nggak apa-apa, ini karena saya terlalu ambil lah.
Harus biasa teman.
Ya udah dulu nanti.
Yang setengah banget yang atas Pak ya? Yang bawah sih nggak terlalu.
Nggak apa-apa Pak, selamat. Biar agak putihan.
Udah pakai citra.
Yes.
Indonesia untuk disposisi dari itu terkait pembiayaan itu diskusikan besok pagi ya. Pembiayaan
PPGS
OR
OR pribon.
diskusikan besok jam 10.
Oh ya, udah kok sebenarnya udah beres, kemarin saya udah diskusi Mas Darwin.
Udah.
Itu udah sesuai dengan yang memang kita biasanya.
Terus yang
Kemudian,
terkait pembiayaan sertifikasi itu
ikan itu udah pembicaraan biaya pelatihan dan sertifikasi. Tapi kita kan hanya nanggung SPT sama si pengusulnya, cuma di situ memang ada honor. Selama ini kan yang masih honor, tapi yang masih SPD. Nah, tapi seperti itu kita nggak honor.
ya kalau ngasih honor jadi nggak independen.
Nah makanya selama ini kita nggak pernah ngasih honor. Jadi memang ngasih SPD. Cuman kemarin masih bangga ini. Mereka kan banyak sekali Pak. 2 penguji, 4 pengawas, 4 pengadministrasi. Loh kok banyak amat gitu Pak. Terus kalau yang lalu kan kita ngasih 8. Nah besok saya mau sama semua lah, paling kita kasih 6 gitu kan. Tapi nanti ya harusnya gitu maksimalnya sampai 8 nggak apa-apa. Jadi 2 penguji, 3 pengawas, 3 pengadministrasi udah cukup lah gitu. Nah, nanti kalau kurang-kurang kenapa dibantu sama kami gini gitu aja. Pak TB-nya udah ini juga kok udah nggak.
Pesertanya juga nggak banyak kok.
Lumayan kalau peserta mah.
Nah maksud saya tuh dengan itu masuk
Ya itu namanya 3 hari. Kan 2 hari dia minta 3 hari. Maksudnya bisa 3 hari SPD. Ya. Karena SPD kan waktu sekarang SPD kan masih mau, tapi SPD full gitu ya.
Untuk itu ya bisa masih
Karena kalau dia ini memang nggak bisa. Yang di dalam aja nggak bisa
itu waktu itu ngomong masalah undang lebih sama baik kok. Sekarang aja kita diskusikan. Apresiasi juga aja. Apresiasinya mau seperti apa? Kita nggak usah istilahnya ini. Kita coba dengerin dulu.
Iya, pokoknya iya.
Itu aja. Kalau nggak usah dengar dari Wadir 2 itu kan akan dihitung berdasarkan kelebihan.
Dibatasi sama Bu Yuni.